How many of you are familiar with CERT?
SFL?
Computer Emergency Response Team.
No.
It's an organization that's primarily based in the U.S., but it's international in, what do I want to say, reach, international in perspective. It looks for and issues bulletins about known threats to computers, to computer systems, to computer networks. And it does this on, I get these emails about, on a regular basis, I get them, I think, once a week. And then if there's an emergency or some other new threat that's just been detected, I get an alert right away. And this organization is doing their own experimentation and their own testing with their own engineers, but also they receive input from people like Norton, McAfee, Avast, and so the other large commercial anti-threat, anti-spyware companies feed into this organization. And I put this up because everybody in here theoretically is interested in networking and may or may not be working in networking in the future. This is one place you definitely want to keep an eye on. It's, see, the CERT is Computer Emergency Response Team. It's based on the National Cybersecurity and Communications Integration Center, which is, definitely you can tell by the symbol, right? It's a U.S. organization. But, like I said, it's international in scope. And off the top of my head, I don't remember the European equivalent, but they work together. And the reason why this caught my eye is this alert that came out, this bulletin, specifically is about securing end-to-end communications. Now, if you're interested in these, you can go and you can sign up. You do a search in Google for CERT, and it'll take you to the homepage. And you can sign up to get alerts. It's free. They don't care. Their philosophy is the more people that are educated and aware of security and security threats that are out there in the world, the better off all of us are, because that's more people that will be taking steps to make sure that these threats don't explode in the wild and endanger entire networks. This one, as I said, caught my eye because of the securing end-to-end communications, and then given my tremendous fondness for Microsoft, you'll see that just about all the errors are with Microsoft. So I thought that was particularly pleasing. You'll see the release date. This is today. This came out today. Systems affected, network systems. And this is sort of the format that these reports take. They all have a number, so there's a large repository you can go and look up. And it's just a big online database that you can search through. And in this case, systems affected, network systems. And what caught my eye is they're particularly interested in this alert about this, see where it says MTM here? Or MITM, I mean? Man in the middle. Remember talking very early, the first week, about threats to the network, and I was talking about people being in the middle and stealing, in effect, an IP address and inserting themselves in the conversation. And one of the reasons for sequence numbers, aside from the liability and all that, is sequence numbers can help protect at a real kind of fundamental level against that, because odds are the man in the middle may not have the sequence numbering transactions correct. In other words, they may find the proper sequence number to use, but there may be retransmissions or other recoverability going on that will foil them. But that type of attack is called a man-in-the-middle attack. And they're very common. I was talking just Tuesday about the war driving, right? Everybody remember that? One of the goals behind war driving is that it allows the bad people, I don't know what you call them, bad guys, right? It allows the bad guys to find networks in which they can insert themselves. Generally, they're not after the person who owns the network or anything, but they're after taking control of the systems that are on that network to set up more advanced attacks like the distributed denial of service attack. So you use a man-in-the-middle attack to co-opt one or more machines on an unprotected network or one or more unprotected machines, and then once you've installed Trojans on all of those, at some point, whether it be a timed event or it's a directed event from a master server somewhere, all of those systems wake up and started issuing an attack. And they use a denial of service attack to try and extort money out of large corporations. I mean, you launch a distributed denial of service attack against a Yahoo or a Google, odds are, if you're very good at what you're doing, you can go to them and say, look, give me $2.5 million and I'll stop it. And I'll turn it off. And companies pay. They don't publicize the fact. They don't talk about it, because the last thing as a public company you want to do is be known as a company that can be extorted, right?
Security.
But they pay billions of dollars a year. Gets paid to people that are performing these sorts of attacks or are performing the other ones that we talked about, which were the encryption attacks. They come in and you get a piece of malware on your computer and it just goes out and arbitrarily encrypts the entire hard drive. And then you get a nice email saying, oh, by the way, we'll give you the key to decrypt everything and recover all your data if you give us $20,000. Well, hit 200 or 300 people in a corporation with that kind of an attack, and now you're talking about some serious money. And again, it starts with perhaps somebody using this man-in-the-middle attack. So anyway, this alert gives you a description of how it happens. It hurts too, but how it happens. And you'll see under the description there, when a third party inserts itself between the communications of a client and server. And while that sounds difficult, it is not. And not only is it not difficult, but you probably don't have to write any code to make this happen. The code sets are out there in the wild, and you can probably get them for free. Because there is this market of free code that's provided, and you hear terms like script kiddies or script jockeys used in a nasty way, and that refers to the people that are going out and lifting these open source type code kits from the internet and then using them to try and perform bad actions. And the reason why they're called script kiddies is because they don't know what they're doing. They're just getting hold of this code and then they get instructions on how to make it work. What the script kiddies don't realize is, at the same time that they're using this code to attack somebody, now their machine's being taken over. And they become part of a much larger network. And the sources of most of these attacks, I think it's still safe and still true to say this, but most of these attacks, these types of attacks, man in the middle and then the sort of encryption, disk hostage and those types of attacks came out of Russia and came out of Eastern Europe. The attacks that are originating, most of the stuff that's originating in China today is either large-scale distributed denial of service attacks or hardcore deep-level hacking where they're going in and they're doing corporate and or national type espionage and breaking into systems and looting information from very, very deep repositories within entities, corporations, or nations. But if you go through, and we'll wind this up, you go through this attack, they give you all this stuff about it. One of the, after they tell you what's wrong, they tell you the solution. The solution in this case is to update transport layer security and secure socket layer, TLS and SSL. One of the, I won't say it's a task that I dislike, but just a task that seems to me to take more time from me than it could be better spent doing something else. Instead of looking at Nathaniel's code, I got to be putting maintenance on systems. It's that kind of thing. People have that attitude. That's a real common attitude. It's nothing against you, Nathaniel, and sorry for picking on you, but I'm not trying to. But, it seems unproductive, it seems like a waste of time, it seems like a lot of effort, and it can be to put maintenance on systems. Windows is, I told you the horror story about Windows 8.1 on Tuesday. Linux can be particularly bad. Ubuntu, periodically Ubuntu, because it's built on Debian, will have a Microsoft type update scenario where you have 40 or 50 updates that need to be done. I mean, right now I've got four or six pending for my production machine. So anyway, the long and the short of it is people put off putting on maintenance, and then what happens is they have back level implementations, code sets that have these exposures in them, and they ignore stuff like updating TLS and SSL. And then further down, they give you more detailed analysis of how to fix it, but further down, where is it? Well, maybe it's on the website itself. If you go and look at this, it calls out all of the, I'm going to cancel that. If you just go and look at it, it calls out all the Microsoft products that have the exposures in it, and in addition to updating the security, which should, in the short term, halt the attack or at least lower your vulnerability, then you've got to go back and you want to update all those products. And part of the burden of doing maintenance on systems is not everything applies to you. But when you get bulletins, especially this type of bulletin from these folks, you go and look at it, and it takes you maybe 5 or 10 minutes to research every product to see whether or not you have the exposure. And so it can be a tremendous time sink. Okay. Anyway, enough about that. This caught my eye. It was securing end-to-end communications, and I thought, well, we've sort of talked about threats, and I thought I'd put this up there, just make you aware of it, so that you can look into it. These are also the folks that issue the bulletins for consumer laptops. And it's their bulletins that turn into the fix packages or the update packages that come down from the Nortons or the McAfees or the Avasts that update the virus definitions on your systems. And Apple, as much as they would like to claim they are not exposed, is just as much at risk and as vulnerable as Microsoft systems anymore. Especially, the latest thing is the Apple Watch, right? You might as well be advertising the fact that you're a candidate for phishing. And this is absolutely true. The current work that's being done in the phishing and the malware industry, and it is an industry, it's a multi-billion-dollar industry, is concentrated on Apple products, specifically the Apple iWatch. And hacking the iWatch, because what's the iWatch connected to?
Your phone.
iWatch is connected to your phone. People think about at least putting security on their phone. Nobody's thinking about putting security on the iWatch. And once they compromise the iWatch and they get to your phone, now anything that your phone connects to is compromised. So just because you have an Apple product doesn't mean that you're safe. Enough about that. Get off the soapbox. Okay. All right. We left off with reliable data transfer. We just started talking about RDT, right? RDT, for the purposes of this class, RDT is referred to and is talked about in the book as a protocol. And it is and can be a protocol. It is a proprietary protocol that we're going to implement between client and server. And Nathaniel's implementation may be different from Stephen's implementation, may be different from Jonathan's implementation, but they are out in their own right protocols. Why? A protocol is something that defines the interaction between two, in this case, end systems. All right? And why are we looking at reliable data transfer? Because not all networks are protected, are dependable. And we've talked quite a bit about an undependable network topology. And what one is it? This would be the class interactive. Come on, somebody guess. What is a network topology or a network transport that does not have any reliability built into it? We just talked about it Tuesday. I'm old. I'm supposed to be forgetting stuff, day to day. You're not. Connectionless transport, right? UDP. UDP is best effort. I'm going to put it on the wire. I really don't care if it gets out to the other end or not. Who cares? As soon as if I'm a UDP state machine, man, as soon as I put the traffic out on the wire, I can go back to sleep. I don't care. So, in those cases, we need some sort of reliability to guarantee that our use of the network achieves the goals that we want. So reliable data transfer, talked about in the text as a protocol. It is not an official, a formal protocol, but it is a protocol nonetheless. And these are the conventions that we'll use for the next discussion over the next probably couple of days at least. This will be an ongoing project. One of the reasons why we're doing getting you set up with an AWS workspace and all that is because you will be writing a server-client application, and then that server-client application, over time, you will implement or enhance it with more reliable, dependable communications. So you write your server-client communication project, and the very first time you're going to be concentrating on the server part and then on the client part, and you'll probably want to select, for purposes of making sure that your server and client applications are okay, a reliable transport. So we use the stream socket. In other words, you're going to use TCP, but then we're going to have you use UDP, which is just the datagram socket, and because it's undependable, it's best effort, you're going to implement the reliable data transfer state machines at both ends. Okay. The convention is above the red line, above the line is the event that's going to cause a state transition in the state machine. Below the line is going to be the action that results from that event. Pretty simple, right? And we'll talk about how states change in the following diagrams. So, RDT 1.0, reliable data transfer. If we assume that the underlying channel is perfectly reliable, then we really don't need anything to implement reliable data transfer. Okay. We can count on the network layer, at least, to provide that. If not, network layer, maybe the physical layer, who knows? The link layer. Could be any of the underlying layers. So, first version of your RDT state machines will just be machines that effectively indicate in the return codes or in some fashion that they're there, they are inserted as a shim between your client and your server in the underlying network layer, or underlying transport layer, really. And 1.0 is just demonstrate that they do indeed exist, that they handle the packet somewhere between the application and the transport layer. Okay? Not real difficult, not real hard. You'll have a separate FSM. Everybody understand FSM? Functional state machine. State machine is a piece of code that theoretically changes amongst or between a number of different states as it's performing actions and as the result of actions. So this slide here is just the conventions that will be used in the following discussions. Very simply, the first thing it's going to do is your application layer is going to send a packet. Okay, send some sort of data. And your FSM is going to insert itself, it's going to accept that data, that packet from the application layer, it's going to turn around and send it, and then it's just going to wait. Okay? In fact, the very first implementation will probably be unidirectional, in which case it'll very probably be, I would suggest, at the client end, and it just accepts the request, the data from the client, builds the packet, and then sends it on to the server. The receiver, the server end being the one on the right there, and what it's doing is it's waiting for a call from below. What's below? What do you think is below? What does that mean? Probably the transport layer, right? 1.0, we're assuming that we have a reliable channel, so it's probably using what? Come on, you gotta know this stuff. This is fundamental to networking. Reliable and unreliable data transport.
Socket.
What?
Socket.
Well, a socket is how you establish the link between the layers, yeah. But what kind of socket? It's reliable data transfer, a reliable channel. About 7 minutes ago, I was talking about the opposite of this.
Wireless.
No. TCP. Connection oriented. Reliable transmission, reliable transfer of data. So that call from below on the right hand side is probably going to come from TCP. It's going to be some sort of answer, some sort of data delivered to the socket that's been created by your FSM on the server side. Right? Likewise, on the right or on the left hand side, that's on the client side, and it's going to, in effect, it's going to get data as part of a send request. And I say as part because the send request is going to include more than just the data, right? And then as a result of that event above the line, it's going to create the packet, and then it's going to send it. It's not hard stuff. But you got to understand what we're talking about. So, first implementation, you're going to test just to make sure that it works that at both ends over a reliable channel. Why over a reliable channel? Because you don't want to add any kind of complexity first. It's not necessary. Just with 1.0, I want to demonstrate that it's working. All right. 2.0. What are some of the problems that might occur? amongst them bit errors. Anybody ever heard the term bit error? In any particular piece of data. What? It's just Charlie 1 is an A, right? Charlie 1 is, let's make sure I don't screw this up. 1, 1, 1, 0, 0, 0, 0, 1 in binary, right? Right? What's each one of these things? It's a 0 or a 1. What is it? It's on or off. What's on or off? You don't really care about transistor, although if somebody says transistor, they're really good. These are bits. Right? This is what goes out on the wire. One, and all the rest is zeros. Okay? So, what happens if during the transfer we wipe something out and we send, or we receive at the other end what's the Charlie 0? Is that a character? Is that printable? You can look this up, by the way. Every laptop, every operating system provides a character map that will show you what each hexadecimal byte refers to. This is a nothing. It's an unprintable character. You get that embedded in the data stream and results are unpredictable. So what we sent isn't what was received at the other end. Why? Because a bit got turned off. There was a bit error. Now, that's not such a big deal. Instead of an A, we get something else. Odds are that that A is going to be surrounded by other characters. At the other end, if we don't take any corrective action at all, it ought to be pretty easy to figure out what was missing. But suppose that this is a transmission of a transaction between an ATM and a central bank, and what winds up arriving at the central bank is not your withdrawal of $20, but your withdrawal of $2,000. Probably don't want to leave that up to just plain guesswork, right? Because if it's not corrected, you've only got $20, but as far as the bank is concerned, you owe them $1,990, 80 more. And now you got to make your $20 stretch for the next 3 or 4 weeks while they try and figure out what happened. Why? Because there was a bit error that was introduced. So, we probably want to, and this is also, I will tell you, the easiest thing to correct for, we want to make sure that bit errors don't occur. And this is not that uncommon. Any sort of electrical interference will cause bit errors. Odds are at any given point in time when you're using wireless, you're experiencing thousands of bit errors a second. Yeah, okay, thousands of bit errors a minute. But the underlying protocols, the 802.11, is smart enough to to detect and then correct for those. So one of the first things we want to do is how do we recover from errors? Well, we can say we'll implement acknowledgments and negative acknowledgments. That's what that NAC is, negative acknowledgement. Okay? And we use the NAC to say what you thought you sent isn't what arrived. Now there are all sorts of options at the sender end architecturally in case they receive a NAC. One of which is resend the packet that experienced the error. Okay? But how do we tell whether or not we had a bit error? I mean, what is, knowing nothing else, what is the logic you implement on the receiving end to detect whether or not you had a bit error? Remember Tuesday talking about hash values? And every packet that gets sent, every one, has a hash value. We need to look at a trace to look that up. In fact, all of you should or could have the slides from the last week in which there were some trace examples. If you just look at the headers, there is going to be, in this case, depending upon the packet and depending upon the decoder, they call it a CRC value, they call it a hash value, right? But what you do, sender and receiver agree upon some algorithm, some computational processing that takes all of the data in a packet and generates a value from all that data. Send that along with the packet. When it is received at the other end does its own hashing of the data, compares the two values, and if the two values don't agree, sends a NAC back saying, I know what you thought you sent, but it didn't get here. Resend it. Okay? So in our RDT 2.0, we're going to add error detection and receiver feedback. Which side would you add that to? Sender or receiver side? We have our client side, we've got our server side. We'll assume that this is the sender and this is the receiver. Which side are you going to add that to?
Server side.
Say it again.
Server side.
To the server side? Okay, we add it to the server side. So the server figures out that the data it got was not what the server thought, the sender thought he sent. So given what's here, what does the server have to do?
You need to compare the hash value.
Well, it's done, assume it's done all that. It's compared the hash values, it's figured out that there's been a bit error. What does the server have to do? Louder.
Ask you to send again.
And how do we do that?
Whatever.
It's up there.
Yeah, to tell sender that server and retrust it.
We send an ACK. Negative acknowledgement. What you thought you sent isn't what arrived. The architecture, the application architecture that includes the network architecture for the application is that receiving a NAC, we're going to retransmit the last packet, right? We've already established that. Okay, this is heading back, and what arrives here is that. heck is this? I have no idea what this is. A nick? What is it, nicotine? Knick-knack? What the heck is this? We've implemented the checking over here on the server side. What does the client side do? Well, it probably blows up. Right? It's a Microsoft product, it blows up. So when we implement this sort of bit error checking, we probably want to do it what? On both sides, right? Make sense? It doesn't do any good to just have one side checking for bit errors, because logically, if there's a bit error that has already occurred on somewhere between communication, if there's already been a bit error that's occurred on the communications link between two endpoints, odds are that that bit error is not going to be only in one direction, right? I mean, it's possible. That's an ugly network problem that we won't get into right away, but it is possible that bit errors can be unidirectional in nature. So we better implement it on both sides, right? So we get down here, or on the client side, we received a NIC. We have no idea what that is. What do we have to do? We've implemented our bit error checking here. What do we have to do down here?